In this short video, I'm going to introduce the circular platform challenge, and in another video, I'll have the solution. So what you're looking at here is a circular platform that can rotate around at a constant speed, and that speed will never change at all throughout the entire problem. This platform, kind of like a record player, if you will just be going around and around and around forever and ever at some constant speed. Now on this platform, the surface is rough. You can think of it maybe like sandpaper, and there is a coefficient of friction. In this case, I've written down the variable mu s for the coefficient of static friction. And remember, static friction is when the object is not allowed to slide and move relative to the surface. And that's what we'll be seeing here. In this problem, we've got a block over here at point A. And right now, you can visualize that it's just moving around in a circle. It's not sliding on the friction surface. It's on the friction surface at rest with respect to kind of the sandpaper, if you will. But it is moving around in a circle, of course, in physical space. All right, so that's what you're imagining. Maybe another example could be a record player, and I don't know, put like a coin or something on the record player and watch the coin go around in a circle. That's basically what we're looking at here. All right. Now, interestingly, I've parameterized the position of this block to be a distance capital R away from the center of the platform. Now, what's the question? What's the challenge? Number one is for you to derive an expression for the maximum speed v, and that's the tangential speed that the block can travel at when it is at location A. And if it travels any faster than that speed, it will slip. It will not be able to go in a circle. It will slip away, if you will. Okay? You can hopefully imagine that happening. So that's question number one. And anytime you kind of derive a formula like this, you want to do it in the most simple variables possible. So the variables that you see in the problem here are variables m. We'll put m for mass, for the mass of the block. So that's a possible variable. Of course, we're in a gravitational field g. We know there's some coefficient of static friction mu s, and then we also have a radius capital R. So as you work through the problem, try to write your answer, and you should, at most, with these variables. You may see some of them, all of them, in your final answer. You'll just have to see when you get there. And then number two, that's the first part. Number two, after you get the answer to number one, is you want to use first principles here to prove if the block would slip if you placed it at B. So you need to imagine that this platform is moving around in a circle at the same constant rotational rate forever and ever and ever. You're visualizing the object as it moves at A, and then you place the object at B, and the platform is still moving around at the same rate. In other words, it takes the same amount of time for the platform to rotate 360 degrees. Okay. So if this block here, block A, is moving at its maximum speed, it's just about to slip. Not quite slipping yet, but you're going really, really fast, just about at this maximum speed, right before it slips. Okay, you get the platform to be spinning at that speed. If you could then instantly move this object, pick it up, and then allow it to be over here while the platform is spinning around at that speed that was just set, would the block slip off if you placed it at B? That's the question. Okay? You want to try to prove that using first principles. It's a pretty challenging question to kind of get everything right and to argue in variables correctly and to reason your way through it. But give it a shot, and then we'll take a look at a solution, and I think you'll learn some great things from this problem.